Yeah, good morning. I am Tom Stephenson. I'm the Director of Services and Partnerships at Simul8, and I'm here today to discuss an innovative approach that uses simulation-powered digital twins within a healthcare setting. So just a bit of background about what Simul8 is. So for over 30 years, we've been helping organizations from various sectors, including, defense, manufacturing, healthcare, automotive, to use our platform to improve decision making and optimize processes, increase efficiency, reduce costs, all those types of things. And now, historically, that's been for capital expenditure or large decisions about change, running them through a simulation to see the impact. But now we're a leading developer and innovator of simulation-powered digital twins, which kind of take this technology to the next phase, where we are using real-time data for foresight to be able to make decisions in real time and deliver operational excellence. So this example that I'll get into quickly is a digital twin that's created using electronic medical records, which are the records that update in a hospital as patients move through the system and are used for all kinds of things around where a patient is, but also accessing information for patients. And all hospitals will have electronic medical records of some kind. Now, what we've done is we have used the software that we've worked in collaboration with software specialist Galaxy Creations and layered on top of this sort of real-time mirror by turbocharging it with simulation techniques. And this is going to help hospital planners look into the future and optimize hospital bed management. So let's get straight into it. So what you can see here is a real-time reflection or a mirror of what's happening in a hospital. And this is more of a sort of static twin. It's showing exactly what the situation is right now. It's not only showing where bed bases are full or empty, it's also giving information about, who's in the bed. Is it male or female? Are certain beds dirty and need to be changed? All of this can be seen. And that's, even without simulation, that's really powerful because, at the start of a shift, healthcare leaders are no longer having to walk around the bed bases to understand what's going on. They can just look at this screen that's easy to interpret, easy to digest, and ultimately aids collaboration. And it does that because, you can see where the pressure points are and you can discuss strategies to move those pressure points to maybe areas of lower pressure. That's really good. But one problem that might come by using this is that what if you see the real situation, you've come in at the start of your shift, and you can see that a bed base is completely full. That might not be a problem in its own right, but if that bed base is completely full and there are people elsewhere in the hospital trying to get into that bed base, this is where we may have problems and we might start to see pressure build. So our bed base is full. We need to do something about that. It's a pressure situation. But there's quite a lot of things that we need to do in a hospital before we can get patients out of that bed base. Is the family ready? Is transport available? I mean, ultimately, is an alternate place or a discharge plan in place? Even things like pharmaceutical orders, drugs need to be ready. Some of these might need to be mixed. The pharmacy might not be open in real time, like all the time. They may have different demands. So all of this can kind of create a lot of pressure. And when there's a need to move patients, having to do all these things in a high pressure environment isn't ideal. So if the bed base is full, there's pressure here, but then very quickly that can push back to the emergency room because people are trying to get out of the emergency room into the full bed base. They're starting to then queue here. Patients are waiting longer. And again, we have to do something about this. We must react. And we've got two kind of core options. One is we push people out into clinically inappropriate wards. This one's full. Where else can we push them? This happens to up to sort of 10% of patients a year, and it's not really what you want to happen because that inappropriate ward won't have the facilities or staffing, everything else available to suit the kind of ailment that you have. So things like length of stay is going to increase, readmission, and mortality is going to increase if this happens. So we want to avoid that. The other option is, well, we don't want that to happen, so let's wait. Let's let our emergency room kind of get fuller. Let's let more patients wait here. And again, worse kind of outcomes, more mortality. So none of these situations are great, and it's something that we may have to kind of scramble to avoid. Now, what we're trying to do when we introduce the simulation digital twin is tell us what if we knew this situation was coming 12 hours before, so we've actually got time to kind of deal with it. This is the simulation that's set up, and what's going to happen first of all as I hit the run button is you're just seeing this kind of tracking the real-time movements. So as patients move, there's going to be a update in the field of the electronic medical record, and that's going to signal to the simulation that a patient's moved. Now we use like Python scripts to draw the information from the electronic medical record and push that into the simulation. But critically, what's happening is as those patients move, key things like how long they stayed, where did they go next, at what time did they move, are all tracked in the background and held. So that means when we run forward, which is what we're trying to do now, we'll run forward from real time, we can extrapolate how patients have moved in the past with similar conditions and use that to project forward. So what we do now is we come from the current time and we run forward, and the first thing that's happened is it says in 26 hours we're going to have a problem. So we want to see how big a problem is that, and that's where we ran it through for 3 days in this case. You can run forward for as long as you want. Now, what we've kind of seen by running forward is that this bed base has been full. There's actually been 3 patients trying to get into the bed base who can't. And if we think about our emergency room, has that coped because of that? Because that might not be a problem if the emergency department has the capacity to cope with that. But in this case, the wait time has been longer. So this is where, because we've seen we need to create space for 3 patients, we can start doing all of those things that we needed to do to get patients out much, much sooner. So this is where being able to project forward really, really helps. Now, coming from there, this is where we get to kind of what is, and we move to what's next. So what's going to happen next? But ultimately, what we then use the simulation for is testing lots and lots of options. So if we do push patients this way, if we increase staff here, if we change shifts, what is going to give us the best outcome? And that's where we next use the simulation. Ultimately, we're trying to get to what's best, and this is what we've done with other simulations. It's what we're working to now, where we automatically run lots and lots of scenarios and just prescribe what to do next in that situation. So that's where we're getting to. There's been a lot of detail kind of thrown at you. Happy to kind of follow up if any of that you want more detail about. And ultimately for us, that was a healthcare example, but probably we see this technique used most in manufacturing, where we maybe need to make sure orders are fulfilled, or we need to respond to a breakdown and that type of thing. So it can be used anywhere. We see it used in manufacturing a lot, but I'd invite you to think about how it could be utilized in your particular industry or sector as well. And thank you very much for listening. I hope I've stayed within the 8 minutes.
Tom, our first question for you, please, is what ontology are you using behind the scenes to model a hospital?
Yeah, so I'll go into a bit of detail about different areas. So in terms of the patients that are moving through, we're generally looking at, all the characteristics which are going to be important to flow, which is always going to be condition, age, acuity level, those types of elements. And in terms of like the flow between different areas, we're looking really at when we segregate patients in that way, how have they reacted in the past, and we assign that to kind of distributions. So we're, not everybody's going to be the same, even if they fall into those same buckets. So we create distributions to show like the likelihood of, if you're part of that segregation, what is your journey going to create? And then we run something called a trial, which is doing lots and lots of different runs with sampling from that distribution to see kind of what the ranges are that are going to be the results. So we're not just giving one answer that's going to be like the average waiting time is going to be this. We're giving an answer that's saying the average time is going to be between X and Y, and we're 95% confident that that's going to be the case. So by applying that data, that allows us to get to a kind of level of accuracy that we hope will be useful, a lot better for kind of, projecting forward.
Tom, our question back to you, if we could please, is can you comment more on the type of models you use for simulations? Is that a type of machine learning model? This will be interesting as any medical procedures require the patient to go through a process, for example, several wards for treatment.
Yeah. So, I mean, right now, the way this is working is we've almost written our own kind of way of tracking what's happened in the past and to kind of look at what's moving forward. But we are kind of in R&D phase here. So we're trying different machine learning models actually to assess whether they're more accurate than kind of what we've got now. And we're doing them in two different areas. One is to decide kind of what's next. So we're looking at, can we predict what's next using different machine learning models, and we're using Python scripts to run them through. But also when we get to the kind of what's best, we're looking at different machine learning scripts there as well, to kind of, in the same way kind of chess computers work, where they're saying in different situations, you get a better score if you've done a certain thing. So we're looking at those types of machine learning algorithms as well. The good thing is, because as the simulation runs, we're collecting more and more information. Kind of the longer you run, the more information is available to the machine learning algorithm, which is going to allow us to continue to kind of improve it. But that's very much something that we're researching now to try and get the optimum machine learning algorithms, especially when we want this to apply to different hospitals.
Very good. And a link question here, which you've in part answered already, but just to add a bit more, if you could, Tom, is how accurate is a simulation? Is it being benchmarked / validated? Are the simulations using AML algorithms?
Yeah, so I mean, we are certainly validated against one hospital to start with, and it's relatively accurate, but we do feel like we will get more accuracy with different machine learning algorithms. So that's where we're testing things at the moment. We're trying to see what's the best way to get the most accurate run forward, and we do think that there's going to be certain machine learning algorithms that are going to help a lot with that. So certainly, if anybody's got any ideas around kind of how to best implement that, we'd be interested in discussing that.